Okay, so let's try and work out what we would expect the relationship between the number of things we see and their brightness to be. So we've got a whole bunch of gamma ray burst sources, whatever they are, spread over space. We'll make two assumptions, which we'll come back to later. Assumption number one is these are spread uniformly in space. So they're not concentrated close to us or far away from us, they're just equally distributed all over space as far as we can see. And assumption number two is they all have the same luminosity. Now, neither of these are true, but let's assume them for the moment and see where it takes us. Now in this case, let's say Earth's here. We're going to be able to see things out to some radius r. If a gamma ray burst source has a luminosity L, the flux we see is just L over 4 pi r squared. R is the distance to it. What this means is that if we see an object, its distance is going to be proportional to flux to the minus a half by rearranging that. So what this means is the faintest ones we can see be right at the limit of sensitivity of a telescope. At a brighter flux level we're going to see only closer ones in. So given the luminosities are assumed to all be the same, that means r must be smaller. We have that flux is proportional to 1 over r squared, so we rearrange this and get r squared is proportional to 1 over flux, so r is proportional to flux to the minus a half. So what this means is we can't see if the flux is larger, so it appears brighter to us, it must be closer in. Common sense, really. Now let's look at the numbers we see. We're assuming the density is uniform everywhere, so the numbers we see is going to be proportional to the distance out to which we can see them, cubed, because it's a volume. The numbers are proportional to the volume that we are surveying. The bigger r, the larger the volume, so that's equal to 4/3 pi r cubed, the volume of a sphere. So what we have is the number we can see is going to be proportional to r cubed. But we know that r is proportional to f to the minus a half, so we end up with a number that's going to be proportional to this cubed, so the flux to the minus 3 over 2. So what that's telling us is that if our two assumptions hold, if we see a brighter one, it must be closer, according to this equation here. And if it's closer, we can only see things of that brightness over a smaller volume, so we're going to see less of them. So it's going to tell us that as you get brighter observed flux, the number should go down as the minus 3/2 power. Now, as we saw in the plot, that's actually not what we get. We have number versus flux, and here's the minus 3/2 power as a log plot, and here's what we actually observed. So it's not fitting that curve, so one or other of these two assumptions must be invalid. If we relax this assumption, number 2, that all have the same luminosity, it actually doesn't help us. Because let's say the luminous ones, the fluxes are all going to be bigger because L is going to be bigger. So you're going to have a different constant here. Faint ones, luminosity is small, so you have a small different constant here. But nonetheless, it's always going to have a number proportional to f to the minus 3/2. So it might be one of these for the luminous ones, with some constant in front, and a different constant in front of f to the minus 3/2 for the faint ones, or intermediate ones, or whatever. But nonetheless, if you're adding up a whole bunch of things, each of which goes as f to the minus 3/2, your answer is going to go as f to the minus 3/2 as well. So actually, we can get rid of that assumption. Our answer is the same. So if the numbers are not going as f to the minus 3/3, the only possibility is that these things are not spread uniformly in space.